So, hi everyone. Today we have Priyanka with us. She is going to talk about efficient algorithms for synthesizing T count and T depth optimal circuits. Priyanka is she graduated from CQT and now currently doing her postdoc fellowship with IQC. So maybe without any further delay, I'll let Priyanka take over and let continue the talk.
Okay, hello everyone. Greetings from Waterloo. So I'll be talking about efficient algorithms for synthesizing T-count and T-depth optimal circuits. This talk is based on the results from two of my papers, which have been co-authored with Michele Moschka and Vlad Gargiu. So this is roughly the overview of my talk. I'll be introducing some essential preliminaries and concepts. I'll talk about channel representation of unitaries, and then I'll describe some provable and heuristic algorithms. Okay, so some essential preliminaries. So first, let me describe what is a quantum circuit synthesis algorithm. So in a circuit synthesis algorithm, the input is a capital N cross capital N unitary, where capital N is 2 to the power small n, where n is the number of qubits. And the goal is to give a decomposition of U into a sequence of gates, which usually belong to a universal set. And some further constraints are imposed, for example, to optimize a certain number of resources like T gates or T depth. And then we usually call it a resource optimal synthesis. Here, I'll point out the difference between resynthesis algorithms. So in resynthesis algorithms, the input is a quantum circuit, and the task is to reduce the number of T gates, but not to like optimize it. So, and usually in the resynthesis algorithms, when they give the time complexity or anything, they do not count the complexity of generating the circuit in the first place, which is usually exponential in the number of qubits. In this talk, I'll only talk about synthesis algorithms and I'll not go into resynthesis algorithms. Okay, now suppose U dash is the unitary implemented by the decomposition, that is by the gates obtained in the decomposition of a synthesis algorithm. Then depending upon U dash, there can be two kinds of synthesis algorithms. One is an approximate synthesis where U dash is not exactly equal to U, but it is at most epsilon distance from U. Another is exact synthesis where U dash is equal to U up to some global phase. And it has been shown by Giles and Selinger that if U is exactly implemented by a Clifford+T gate set, then it has certain properties. For example, the entries belong to the ring Zi1 by root 2. At most, one ancilla is sufficient to implement this unitary, and no ancilla is required if the determinant satisfies certain criteria. Now, as I said, that the gates which are in the decomposition of this unitary, they usually belong to a universal set. So I know like most of you know these things, but a quick recap. A universal gate set is a set by which it is possible to approximate any unitary operation to arbitrary accuracy. For example, the Clifford+T is a very popular universal gate set. So let's look into this Clifford+T set. Now we know the n-qubit Pauli operators are the tensor product of the single qubit Pauli operators. And the n-qubit Clifford operators, they belong to the group generated by the Hadamard gate, the phase gate, and the C0 gate. And the n-qubit Clifford+T operators, they belong to the group generated by the Hadamard gate, T gate, and the C0 gate. So the n-qubit Pauli operators are a subset of the n-qubit Clifford operators, which are subset of the n-qubit Clifford+T operators. So as I said, the Clifford+T operators is a universal gate set. Not only that, they are a fault-tolerant gate set, which means they have a fault-tolerant design in most error correction schemes. And this is required to deal with errors which occur due to noise on quantum information, faulty quantum gates, state preparation, faulty measurements, etc. And this is very significant for long computations, else the error accumulates in such an extent that the output becomes unreliable. Now, the Clifford group gates, they have a transversal implementation in most fault-tolerant schemes. For example, this is a transversal C0 implementation between two logical qubits which are encoded with the Steen code. But the non-Clifford gates, like the T gates, they usually require large ancilla factories and additional operations like gate teleportation and state distillation, which are less accurate procedure and they require more time and space. In a word, they are more costly. So it is important to reduce the number of T gates or T count. And it has been shown by Fowler that a fault-tolerant circuit's runtime is directly proportional to its T depth. So it is also important to reduce the T depth. Now I'll briefly explain the T count and T depth of unitaries. Now for a circuit, the T count is the number of T gates in it, and the T depth is the number of stages where the T or the T dagger gates, they act in parallel. For example, this is the circuit of a Toffoli gate, T count 7, T depth 3. Now for the unitary, the T count is the minimum number of T gates in a Clifford+T circuit that implements it. And the T depth is the minimum T depth of any Clifford+T circuit that implements it. And this may change with the use of additional ancilla qubits, measurements with classical controlled operations, and so on. So here we will deal with two problems. Problem one is to compute a T count optimal Clifford+T circuit for an exactly implementable unitary U. So in many cases, we can solve another variant, which is count T, where we are given the unitary and we have to determine the T count, or in the decision version, we have to determine if the T count is at most some positive integer m. And it has been proved by Gosset, Kloshnikov, Moshka, and Russo that if we can solve count T, then we can synthesize a T count optimal circuit with overhead polynomial in the T count and dimension of U. In problem 2, we are required to compute a T-depth optimal Clifford+T circuit for an exactly implementable unitary U. And in the decision version, we are given the unitary and a positive integer, and we have to decide if the T-depth is at most D. Now, a quick recap of some previous relevant results. These are like the best results for these problems before our work. So for T count, a provable meet in the middle algorithm was given by Gosset, Kloshnikov, Moshka, and Russo, which solved count T with space and time complexity exponential in capital N and M, that is order n to the power m. And m is here the T count of the unitary. And this algorithm was parallelized by Di Matteo and Moshka using deterministic walks, but they suffered the same asymptotic complexity. In T-depth, the previous best result was given by Ami, Mashlov, Moshka, and Rotaler, which used the meet in the middle technique and the synthesized T-depth optimal circuits with a complexity 2 to the power k n square whole to the power d. This d is the T-depth and k is some constant. Okay, since all our algorithms, they use channel representation of unitaries, so I'll describe the channel representation first. So given an n cross n unitary, the channel representation is a n square cross n square matrix where the rows and columns are indexed by n qubit Pauli operators. And the R and Sth entry of this channel representation matrix is given by this quantity trace of PR, U, PS, U dagger divided by 2 to the power n. And this is derived from the fact that the n qubit Pauli operators, they form a basis for the space of all Hermitian n cross n matrices. And if U is unitary, its channel representation is unitary. It respects the multiplication law and it respects the tensor product. Each entry of the channel representation is real. So if U is exactly synthesizable, that is if its entries belong to the ring Zi1 by root 2, then the entries of the channel representations, they belong to the ring Z1 by root 2. For a Clifford operator, it is very easy to identify the channel representation because it will have one non-zero entry in each row and column, which is equal to plus minus 1. Now, for any non-zero vector in this ring Z1 by root 2, the smallest denominator exponent is the natural number k, such that we can be written as a plus b root 2 divided by root 2 whole to the power k. For the SDE of 0 is 0. And for a matrix, the SDE is its maximum SDE of any of its entries. For a Clifford operator, the SDE is 0. For single qubit unitaries, this has been proved by Gosset, Kloshnikov, Moshka, and Russo that the T count of the unitary is exactly equal to the SDE of its channel representation. Okay, now if U is exactly synthesizable, then we can represent U as an alternate product of Clifford's and T gates, where T or T dagger gate. Okay, now if we just club these operators together, then we can have this compact representation of U as a product of RP operators and Clifford's, and a Clifford at the end. This RP, when we expand it, it takes this form. R dagger P is RP, actually the adjoint of RP. And if we, these things have been actually derived by Gosset, Kloshnikov, Mosca, and Rousseau mainly, and we further extended it. And if we expand this RP operator further, we can see that the T gate is hidden in it. Thus, each RP operator has T count 1. And in the channel representation, these things become multiplicative and the global phase that goes away. So now let's look at the structure of these RP matrices. Okay, and these things have been derived in our paper with which has been co-authored with Michele Mosca. So this is RP. So the diagonal elements of this matrix are either 1 or 1 by root 2, and exactly half of the diagonal elements are 1 by root 2 and the rest are 1. So for the channel representation of y by yx, which is a 16 cross 16 matrix, so we can say like exactly 8 diagonal elements are 1 by root 2 and 8 of them are 1. And if a diagonal element is 1, then every other entry in the row and column is 0. If it is 1 by root 2, then there exists exactly one entry in the row, which is 1 by root 2, and one entry in the corresponding column, which is minus 1 by root 2, or vice versa. And all other entries are 0. For example, this is in this matrix, we can distinguish these patterns, these 4 squares. Okay, and wherever there are no entries written, it means all these elements are 0. So what happens? We can represent this matrix by an array of length n square by 4. We can just store the pairs of the form j plus minus k, which will imply that the jth diagonal is 1 by root 2 and the jkth element is plus minus 1 by root 2. And we do not need to store k minus plus j because it will imply the elements of that row. So for example, this whole matrix, 16 cross 16 matrix, can be represented by this array of 4 tuples. The inverse of this matrix is very easy to obtain. We just flip the sign of the off diagonal elements. Now suppose W is a matrix which is obtained by multiplying another matrix V by the channel representation of RP. So this multiplication can be done very efficiently. So suppose the diagonal element is 1, suppose the ith diagonal is 1, then what happens? The ith row of V gets copied into the ith row of W. And suppose that the ith diagonal element is 1 by root 2 and the ilth element is 1 by root 2. Okay, so what happens? So that will imply that the lth diagonal is 1 by root 2 and the lith element is minus 1 by root 2, say. So this will imply that the wij is equal to 1 by root 2 vij plus vlj, which means like the ith row of W will be the addition of the ith and lth row of V uh, multiplied by 1 by root 2, and the opposite sign will hold for the lth row. So that's this and this will imply, and this implies, which is like crucial, that the SDE of W differs from the SDE of V by at most 1. And this is crucial in order for our heuristic algorithms. So the complexity of this multiplication operation is order n to the power 4, which is much faster than the state of the art, which is much faster than if you would have used the fastest multiplication algorithm which is available, that is by Legal. It would have taken a time complexity n to the power 4.5 nearly. Okay, now as I said that each entry of this channel representation is real. So if it is exactly synthesizable, then the channel representation, they belong in this ring Z1 by root 2. So we can have a very nice data structure for this matrix. We can simply store the elements A, B, and K, and these are like integers. So, and we can perform all the operations, addition, subtraction, inverse, or multiplications just by using this integer arithmetic. So no floating point operation is required. Okay, now before I go to describe the provable algorithms, I'll describe some essential concepts like Gosset labels. So this has actually been given by Gosset, Kloshnikov, Mosca, and Russo. So our provable algorithm has been an improvement on their meet in the middle algorithm. So what is the Gosset label? This is actually like a representative for the channel representation of unitaries. So how we write it? We first rewrite the channel representation such that each non-zero entry has a common denominator equal to root 2 s to the power sd, the channel representation of u. And for each column, we look at the first non-zero entry from top to bottom such that v is equal to a plus b root 2 divided by root 2 to the power sd, the channel representation of w. And if a is less than 0 or a is equal to 0 and b is less than 0, then we multiply the column by minus 1. And then we permute the columns so that they are ordered lexicographically from left to right. And it has been shown that if if two channel representations are such that channel representation of u is the multiplication of the channel representation of v and the channel representation of some Clifford, then they have the same Gosset label. So this is like they act as some representative of some bunch of a bunch of unitaries. Now we can actually store these channel representations according to their T count, the Gosset labels actually according to their T count in some sorted Gosset database. So for any k, this database for T count k unitaries is as follows. So every unitary which has T count k, it will have some Gosset label that will belong into this database. So for any unitary with T count k, there is a unique unitary with in this database which has the same Gosset label, and this database is always sorted according to the Gosset labels. Okay. Now, as I said before, that we gave a nested meet in the middle algorithm for county, which has been an improvement over the algorithm given by Gosset and others. So the input to this algorithm is an exactly synthesizable unitary, an integer m, and c. The c is actually the extent of nesting that we want. And the output is the t count of u if it is less than m or it returns no. Now the intuition of this provable algorithm is as follows. We know that the channel representation of u can be written in this way, the product of the RPs and the product of the channel representation of C0. So what we do is we search for this set of RPs such that the U dagger RP is equal to the channel representation of some Clifford, because we know we can easily identify this thing. So this is more like an exhaustive search. Okay, so first what we do is we calculate the Gosset label and then we pre-compute the sorted Gosset database up till T count m by c. We start with the identity, and then for each Gosset label or each unitary with T count I minus 1, we multiply it by RP. Now we know each RP has T count 1. So that gives the unitaries with T count I, that is 1 more than I minus 1. And we include that unitary in the database if and only if its Gosset label is new. And we maintain the order always. So for example, we start with this identity, we multiply by the RPs, okay, and we include all these unitaries in the Gosset in our database if their Gosset label is new. Now first we check if the T count of the given unitary is at most m by c by simply searching this database. It is ordered, we can check it lexicographically. We can do a binary search. I mean, it is ordered, it is stored lexicographically, so we can do a binary search. If we find it, then we output it. Else, what we do is we start our nested meet in the middle procedure. So what happens is now we check if the T count is between m by c and twice m by c. In the next big iteration, we check if it is between twice m by c or thrice m by c, and so on. What we do is we take the unitaries with in the database which has T count m by c, and then we check if there is another unitary v which has a T count at most m by c, and if we find that, then we can say that the T count of the unitary u is at most the T count of v plus m by c. Okay, so for example here, suppose like we take this unitary which is at the lowest level, so w24, Then we calculate V, which is W2 for dagger U, and we check if there is any other unitary which has the same coset level as V. Here we find W11 has it. So we say that the T count of unitary U is equal to the T count of W24 plus the T count of W11. Okay, and if we do not find it, then we say that the T count is greater than M. So for C is equal to 2, this is actually the meet in the middle for GKMR. Okay, so this is the comparison of the complexity of our algorithm and GKMR. So like we have a bit more space complexity. I mean, we have some reduced space complexity, but an increased time complexity. So if so we managed to obtain a time space trade-off. So if we have less space, so we can actually synthesize bigger circuits with this algorithm. Okay, so now we give a provable algorithm for T-depth. So we applied this nested meet in the middle technique to find synthesize T-depth, provably synthesize T-depth optimal circuits. Okay, and this work has been done by me with Michele and Vlad. So for this, we first derive a set of some special unitaries. So these unitaries are the product of R dagger Pj such that the T-depth of this unitary is 1. Okay, and we have shown that the cardinality of this set is at most n factorial 2 to the power 3n, like where this the small n is the number of qubits. Okay, so here the input is again an exactly synthesizable unitary. D is the depth, we have to determine whether it is of depth D, and C is the extent of nesting we want. Then the output is a circuit with T depth at most D, or we return no. Now, for this algorithm, we use this result, which is like if Si is the set of all unitaries which is implementable in T depth I, then there exists some circuit with T depth D1 plus D2 implementing U if and only if SD1 dagger U intersection SD2 is not equal to an empty set. Okay, so first we calculate the channel representation of all those special unitaries. Then it's a similar kind of a nested MITM technique. So we calculate the T depth I unitaries with the T depth I minus 1 unitaries by multiplying with Vn. Okay. Now, then we check for this W, which is like the product of Wi's, where Wi's are in Si or S minus 1. If there exists some Wi in Si or S minus 1, such that their coset levels of W dagger U is equal to this W tilde, this product, this unitary, okay? And if so, then we return, else we break. Now, so this is the comparison of the complexity of our algorithm with the previous best algorithm, which was given by Amy, Mashlov, Moshka, and Rotteler, okay? So their algorithm has a time and space complexity, which, well, the exponent was like it also exponential, it was exponential in the depth, but here the base was this Vn, this set of Clifford+T circuits with T depth 1. Okay, this is a large set. The cardinality of this set is order 2 to the power k n square. In comparison, since we use channel representation and these special unitaries, so our base set was this set of special unitaries which had a cardinality n factorial 2 to the power 3n. Okay, and to give perspective about the comparative running time, so what happens? So these are like so if we want to generate this base set like the T depth 1 circuit, like if we can generate the base set, that means we have optimally synthesized any T depth 1 circuit. So this is how it compares with the algorithm of AMMR. Okay, so for 2 qubit circuits, the our base set has a cardinality 122. The generation time is 0.014 second, whereas their base set has a cardinality 11,520 and generation time 1 second. For 3 qubits, our base set has a cardinality to 2,282. Generation time is roughly 2 seconds. Their base set had a cardinality 92,900,000 almost, and the generation time was at least 4 days. They could not even generate any this base set for 4 qubits, and we could generate that, and it had a cardinality say 35,846, and it took roughly some 18 minutes to generate. Okay, Okay, so now we give some much more efficient heuristic algorithms for these problems. So first we give a polynomial complexity algorithm. So previously the provable algorithms all had exponential complexity. Okay, so this heuristic algorithm was given by me and Michele. So here the input is the channel representation of a unitary, and we actually get the decomposition of this unitary. That is, we actually get the circuit for this unitary. Okay, and the intuition is as follows. So we know like this is like this unitary can be written in this way. The product of RPJ inverse times this channel representation of this unitary gives a Clifford. Okay, so what we do is this time we search for the set of the inverse of these channel representations, okay, such that when multiplied by this channel representation of unitary, we get the channel representation of a Clifford. So what we do is we build this tree with the channel representation of this unitary in the root as the root, like we did before. And then what we do is this time we prune the tree. So this is also a exhaustive search, but this time we do a very a considerable pruning of the search space, and that's why we get such reduced complexity. So what we so at each level we group the nodes, which are the nodes are some unitaries if you remember, and so we group these unitaries according some properties, and we then select the group with the minimum cardinality. We chose to study two properties. One is the change in the SDE and Hamming weight, which is like the number of non-zero entries in a matrix. So we studied three types of divide and select rules. In the first case, we divide the unitaries according to the increase or the decrease of its SDE. And when the SDE remained unchanged, we assumed it is undecided. So we selected those unitaries in both the sets. And then we selected the set with the minimum cardinality such that the SDE is at most something, okay, some M dash. I'll explain to you later why this M dash is needed. In the second divide and select rule, first we divided the unitaries according to the change in SDE and Hamming weight. If the Hamming weight remained unchanged, then we divided according to the change in SDE. If the SDE remained unchanged, then we selected those, excuse me, unitaries in all the sets. And then we selected the set with minimum cardinality such that SDE is at most M dash. In the third divide and select rule, we divided the unitaries according to the change in ST and Hamming weight. This time, we considered the unchanged as a different set. Okay, and as before, we selected the set with the minimum cardinality such that ST is at most M dash. Okay, so the algorithm is as follows. So suppose M is the ST of M is initialized to be the ST of the channel representation of this unitary. We know that the channel representation we have already shown can change by at most one. So the T count cannot be less than the channel representation. So what we do is we first test. So this to while loop, it actually first tests whether the T count is at most M. Okay. So for that, what we do is we multiply each node in level I minus 1 by RP inverse, and we note the change in SDE and Hamming weight. If SDE is 0, then we stop because we know we have reached a Clifford, and we return the unitaries in the path. Else we apply the divide and select rule with M dash is equal to M minus I. Why this M minus I? Because we know like the SDE can change by at most 1, right? So what happens is we select those unitaries which has the potential to reach to 0 within the next M minus 1 level. That is, if its SDE is at most M minus I, okay? Now these selected nodes, they become the parents for the next level. Okay, and so on. So we keep testing whether the T count is M or M plus 1 and so on. Okay, so this particular loop, inner loop, it looks as follows. So this is the unitary input unitary. We multiply by RP inverse. Then we divide and select. Suppose these two nodes have been selected. They become the parents. We again multiply them by RP inverse. We again divide and select. So then, then again we multiply by RP inverse. Then suppose we have reached the Clifford here. So we reach the Clifford here. So now we return all the unitaries, all those RPs in the path to this Clifford as the decomposition of U. So U is actually some global phase times RP2, RP3, RP4 times the Clifford. Now our conjecture is the set of nodes which have been selected by the divide and select rule, they include the correct nodes, which means that those nodes that occur in a T count optimal decomposition of the channel representation of the unitary, and the cardinality is polynomial times capital N. Okay, and the complexity, so this gives the complexity of our algorithm, both space and time complexity is polynomial in capital N and the T count of U. Now, to put some things in perspective, it has recently been shown that the lower bounding, the T count of an exactly implementable unitary has the complexity order polynomial in N. So, so in comparison to that, we actually synthesize the T count optimal circuit in roughly this much complexity, okay, polynomial in capital N complexity. Okay, so now we give some implementation results. Okay, so we compare with the parallel algorithm by DiMatteo and Moshka. I mean the DiMatteo and Moshka, this is a parallel algorithm, and they used up till 4096 cores. We used only one core, and we had a serial algorithm. And as you can see, like our time taken by us is also much less. Like for 3-qubit unitaries, it is roughly 5 times less. For 4-qubit adder, so these DiMatteo Moshka, they take 12.5 hours. We can optimally synthesize that unitary in roughly say 7 minutes. And also we synthesize this other unitaries U1 and U2 in roughly 2 hours, or this is like 6 to 7 minutes. And we obtained some better T count than some resynthesis algorithms. For example, this unitary was considered by uh, Amy, Mashlov, and Moshka, like in the T-par paper, they gave a T count 12, we gave a T count 11. Actually, it's not T count. The number of T gates they had was 12, and we gave the T count 11. We also synthesized some random circuits, 2, 3, and 4-qubit circuits with number of input T gates up till 10, 20, 30, and 40. And we could reduce, and our output circuit had less number of T gates than the input circuits. Now, since no algorithm before us can optimally synthesize this huge circuit, so we cannot verify whether our results are optimal or not. But since it reduced the T gates, it's a good indication that our conjecture is correct, and we are able to obtain optimal circuits in many or most cases. Okay, now we give a quasi-polynomial complexity heuristic algorithm for T depth. So this work has been done by me with Michele and Vlad. So here the input is a channel representation of unitary, and we give a decomposition of this unitary such that the T depth is, we give a T depth optimal decomposition of this unitary, okay? So here, what we know is, what we do is, if we club those RPs, if we club these RPs such that each group of RP has T depth 1, which is like each of them belongs to this group of special unitaries, then we can write the channel representation of U dagger in this way. The product of Vj inverse times the channel representation of U is equal to the channel representation of some Clifford, okay? So now what we do is we search for the set of these Vj inverse such that we get this Clifford. So as before, we build the tree with the channel representation of U in the root, and we prune the tree. This time we have 2 kinds of division and selection. So in divide 1, at each level we group the nodes into hypernodes according to a path T count, and then within each hypernode we group the nodes according to some properties or parameters of the unitaries. Then we select the group with the minimum cardinality. Again, we studied the same properties, the change in STE and Hamming weight, which is the number of non-zero entries in a matrix. So I'll explain briefly what we mean by hypernodes and path T counts. So here, for example, this is the tree where this red node is the root, like this is one unitary. And suppose this is another node in this tree, okay? And suppose this node has been obtained by these intermediate nodes by dividing by these, by multiplying by these unitaries. Okay, so the path T count of this node, this non-root node, is equal to the summation of the T count of all those unitaries which occur in the path to this unitary, okay? Now, now the concept of hypernodes. So at each level, what we do is we multiply the channel representation of this unitary with the channel representation of the VIs, which has like T depth 1, but they can have T count at most n, right? So according to the T count of VIs, we can group the nodes in each level, okay, in each into hypernodes at each level. Like these hypernodes, they have the same path T count. So if we multiply by unitaries which has T count 1, then we get the path T count 1, okay. Now each node when multiplied by VIs which has path T count 2, then we get these unitaries which has path T count 3 and so on. And in divide 2, now within each hypernode, we divide these nodes according to their ST in Hamming weight as shown. So this is the algorithm for synthesizing T-depth optimal circuits. So suppose D is initialized to ST U dagger by N. We know like the T count can be at least the SD of the channel representation. So your depth can be at most, your depth can be at least the SD of U dagger by N or the T count of U by N, whichever you know. So again, we test whether we first test whether the depth is D, and then we test if the depth is D plus 1 and so on. So we multiply each node in level I minus 1 by V inverse, where V belongs to Vn. Then we group these nodes into hypernodes and note the change in ST in Hamming weight. If we reach an ST 0 node, then we stop because we reached a Clifford and we return the path. Else we apply divide 2, that is within each hypernode we divide the nodes further and select the nodes such that the STE is at most D minus I minus 1. And these selected nodes become parents for the next level and so on. So this inner iteration, it looks as follows. We have this channel representation of unitary. We multiply by V inverse and we group these nodes into hypernodes. Then we divide, within each hypernode, we divide the nodes further according to ST in Hamming weight and we select the minimum cardinality set. Then we multiply these nodes by V inverse, okay, and divide into hypernodes. And within each hypernode, again, in this case, we find that we have already reached a Clifford, so we return the path to this node, okay. So U is in this case e to the power I phi, which is like the global phase, V1 times V2 times C0. And it has like T depth 2. And here our conjecture is the cardinality of nodes selected within any hypernode is bounded by polynomial in capital N, and the nodes selected, they give at least one T-depth optimal decomposition. So this gives us a space and time complexity polynomial in log n factorial capital N and T-depth of U. It is this log n factorial for which we say like ours is a quasi-polynomial algorithm. Okay, now we compare our implementation results with some previous results. So before us, as I said, that AMMR13 was the best result. So they could, but they had a huge complexity, as I have said before, and they could not optimally synthesize any unitary beyond 2 qubit. We could optimally synthesize up to 3 qubit unitaries, and we obtained much better T depth, like we obtained the optimal T depth, which was not known before. And this has been done in roughly about 30 minutes. And we did synthesize some random 2 qubit unitaries up till maximum input T depth 20 and 3 qubit unitaries up till maximum T depth 7. And like our output circuits had less T depth than the input circuits. Of course, we could not verify whether they were optimal because of the lack of efficient algorithms, but it's a good indication that our conjectures might be correct for most unitaries. Okay, now to summarize my talk, we studied channel representation of unitaries, and this helped us obtain more efficient algorithms for multiplication, inverse, etc. using integer arithmetic. Then we gave some provable synthesis algorithm for T-count and T-depth optimal circuits. We introduced this technique of nested meet in the middle, which gave provable exponential complexity for T-count. It gave a significant improvement in the provable complexity for T-depth. It also helped us achieve some space-time trade-off. We gave heuristic synthesis algorithms for T-count and T-depth optimal circuits. This gave polynomial complexity algorithm for T count and quasi-polynomial complexity for T depth. Thank you.
Are there any questions to Priyanka on the talk? Okay, so if not, let us thank Priyanka for the talk, and maybe we can end the call.